Oops. Ooh, I love this part. The integrals of tangent x, cotangent x, secant x, and cosecant of x. So here are some formulas. And you don't have to worry about memorizing these. I mean, it would be helpful. Maybe it would save you a little bit of time if you at least had a couple of these memorized. I will admit that I don't even bother memorizing the integral of cotangent or the integral of cosecant. Actually, it's possible I may not have any of these memorized because I remember how to derive them if I need to. And that's what I want to show you right now. Okay. I told you in part 1, or maybe it was part 1 of 7.2 that I do try to resist proving too many things. I understand that you're not math majors, all of you. There are certain things I can't resist, and this is one of them. So I am going to show you the integral of tangent Udu and the integral of secant Udu. So let's go back to the tablet. Okay, so I will admit that the formula that I usually think about for the integral of tangent Udu looks a little bit different from the one we were just looking at, but I'm going to show you it's the same. So it turns out that to integrate tangent Udu, you use this natural log rule. So here's how that works. I'm going to write tangent u as sine u over cosine u. Don't forget your du. All right, and now this is going to be a substitution. I guess I shouldn't call it a u substitution because we're already using u. So why don't we make it a z substitution? I'm going to let z equal cosine u, which means that dz is going to be the derivative of cosine u, which is, I hope you said negative sine u du. But I don't want the negative, so let's divide out -1. And that means my sine u du is going to get replaced with negative dz. All right, so look what that gives us. Cosine u gets replaced with z, and then sine u du gets replaced with negative dz. And that looks familiar, right? Integral dz over z is natural log absolute value z. All right, so this is the only thing that's disappointing about not using u for the substitution. I can't use my "but this isn't about you" joke. This isn't about z. It's just not the same. All right. Okay, so that comes out to negative natural log absolute value cosine u plus c. Okay, but if you think back to that PowerPoint slide we were just looking at, it said that the integral of tangent u du was natural log absolute value secant u plus c. Well, that's actually the same thing because secant u is the reciprocal of cosine u. And we were looking at a rule, a natural log rule in part 1. It was called the reciprocal rule. Which said that the natural log of 1 over x is equal to negative natural log of x. All right, so it actually doesn't matter which form of this you use. You can use natural log absolute value secant u, or you can use negative natural log absolute value cosine u. All right, either one doesn't matter. Okay, now we come to one of my favorite integrals, the integral of secant u du. So this is one of those things, and you run into these things in math every so often, that you ask anybody who does what I do for a living, How did you ever figure out the integral of secant? And probably every single one of them will tell you somebody showed it to me. All right. It's not that they figured this out themselves. I don't know who figured this out for the first time. Anyway, here's how it works. So you might think, okay, write secant u as 1 over cosine u. But then you'll find that that doesn't really get you anywhere because you can't do your substitution. You don't have the derivative of cosine u anywhere. Well, it turns out that this is what you do. This is really, really slick. I bet you would agree that secant u is the same thing as secant u times 1, right? That seems pretty innocent. And what I'm getting ready to do is rewrite that 1 in a different way. And I can't believe you didn't think of this yourself. Just kidding. The way that I'm going to write that 1 is like this. I'm going to write it as secant u plus tangent u over secant u plus tangent u. What? Well, just bear with me. All right. So, as I tell my Math C students, you know, when you want to multiply something like this, put a 1 underneath. So, wouldn't that be the same thing? Wait till you see where this is going. It's so cool. As secant u plus tangent u on the bottom. And then upstairs, secant squared u plus secant u tangent u. Now stare at that for just a minute. All right. Pause the video if you feel inclined, right? Because I want you to see if you can figure out where this is going. And it will help tremendously if you remember your derivatives of your trig functions. Okay. You'll find as we go along, it's like, okay, there's something I need to review. There's something I need to review. Okay. Well, it turns out that the thing to do here is another, why don't we stick with z substitution. We're going to let z equal secant u plus tangent u, which is going to make dz, guess what? The derivative of secant u, which is secant u tangent u. Sorry, I have to squeeze this in here. And then the derivative of tangent u, which is secant squared u. Oh my goodness. So except for the order of the terms, look at that. This is exactly what we have right here. That's so cool. So believe it or not, this integral comes out to be in the form, I might be able to finish this on this page. Integral dz over z. All right, so that trick, even though the only reason I know it is because somebody showed it to me, turns out to be exactly the thing that works. So this is natural log absolute value z plus c. In other words, let me box this in here. Natural log absolute value secant u plus tangent u plus c. Okay. No, you don't have to memorize that formula. When it comes time to take your quizzes and your exams, I always suggest, you know, just make sure that you have your formulas and useful things written down on, you know, 2 or 3 sheets of paper, so you know where they are, so you're not having to tear through your notes looking for things. That formula will come in handy every so often, and so there it is. And by the way, the integrals of cotangent and cosecant use tricks that are almost identical. Okay, might be a fun thing to play with if you're bored sometime, you have 15 minutes to kill. All right, so back to the presentation. And we have another couple of examples. All right, so let's look at these. The integral from pi over 4 to pi over 2 of cotangent t dt. And then we have the integral of secant x dx over the square root of natural log secant x plus tangent x. All right, so let's go back to the tablet. All right, here we go. So one of the formulas that we saw on that last slide said that the integral of cotangent t would be natural log absolute value sine t, right? And we don't need the plus c because this is a definite integral. We just need to plug in pi over 2 and then plug in pi over 4. All right, so, and by the way, sine pi over 2 and sine pi over 4 are both positive. So we can ignore those absolute values. The sine, let me show my work here. Sine pi over 2, sine pi over 4. Okay. The sine of pi over 2 is 1. And the sine of pi over 4 is root 2 over 2. Natural log of 1 is 0, right? So we have 0 minus natural log square root of 2 over 2. Now, if you wanted to write your answer as negative natural log square root of 2 over 2, I would be okay with that. Your online homework would be okay with that. But I feel like showing off a little bit, so I'm going to try to pretty up that answer. All right, so we have negative natural log square root of 2 over 2. So by the quotient rule, natural log square root of 2 over 2 is natural log square root of 2 minus natural log 2. And then here's a trick that I use in Calc 2 practically in my sleep. When you have the opposite of a difference, all that does is it just flips the order of the terms, right? So we could just write that as natural log 2 minus natural log square root of 2. However, I am going to write, instead of writing natural log square root of 2, I'm going to write natural log 2 to the 1/2, because now I'm going to use my power rule and go and make that natural log 2 minus 1/2 natural log 2. And when you have 1 natural log 2 and you take away 1/2 of a natural log 2, you are left with 1/2 natural log 2. So I would rather write the answer like that than negative natural log square root of 2 over 2. I just think it looks nicer. Okay. And of course, you could also write it as natural log square root of 2. That would be okay. All right, next example. The integral of secant x over the square root of the natural log of secant x plus tangent x. So I will admit that this problem would be a much bigger challenge if I hadn't shown you where that integration formula for secant u du comes from. One thing we got out of that, let me just remind you what that formula said. It said that the integral of secant u is equal to the natural log absolute value secant u plus tangent u, right? Plus c. Well, with every integration rule, you get a free differentiation rule. So this also suggests to me that the derivative of natural log absolute value secant u plus tangent u is just secant u. So I think I see a substitution in here. why don't we let u equal the natural log of secant x plus tangent x. Okay. And if you're worried about it, I mean, you could, well, except for the fact that we didn't know about natural log back in Calc 1, you could almost differentiate this in Calc 1 using the chain rule. Okay, but I think it shouldn't be that hard to convince you based on that integration rule that we just went over that the derivative of natural log secant x plus tangent x is just secant x. So this integral turns into integral du over the square root of u. And I think we've seen one of those before. That's the integral of u to the negative 1/2 du. So by backwards power rule, add 1 to the exponent, divide by the new exponent, and this time instead of dividing by 1/2, I will just multiply by 2. And this time I can say, but this isn't about u, this is about x. So final answer would be 2 times the natural log of secant x plus tangent x plus c. Isn't that fun? All right, let's see. All right, so the last thing that we have to look at in this section is called logarithmic differentiation. The directions say use logarithmic differentiation to find the derivative of y with respect to the, that should say given, independent variable. Notice that these are both functions that you could have differentiated in Calc 1. They would have driven you a little bit crazy because you would have had chain rule, product rule, quotient rule sort of all tangled together. So the idea of logarithmic differentiation is by introducing logarithms and then using a little bit of easy implicit differentiation, it makes it a lot simpler. So let me show you how that works. Going over to my tablet one last time. All right, so the first function is y equals the square root of x squared plus 1 times x minus 1 squared. And we want to find the derivative of that. So here's how logarithmic differentiation works. Before we do any calculus, we are going to take the natural log of both sides. Now, one thing I have found with Calc 2 is that people tend to get a little bit carried away with natural logarithm. They think that they're supposed to somehow make a natural logarithm appear in every single problem. All right, that is not true. Notice I'm taking the natural log of both sides, so that's fair. And now, before I do any differentiating, I am going to simplify the right-hand side of that equation. And I think I'll keep using red here. So we have natural log y equals, and the first thing I'm going to do is turn that square root into a 1/2 power. So the natural log of x squared plus 1 times x minus 1 squared to the power 1/2. I use my power rule for logarithms and go, all right, make that 1/2 natural log x squared plus 1 times x minus 1 squared. All right, and now I can use the product rule for logarithms. See, I'm trying to make the differentiation part of this simpler. Okay, so this is going to be 1/2 times the natural log of x squared plus 1 plus the natural log of x minus 1 squared. And then I'm going to do just one more thing. I'm going to use my power rule for logarithms one more time and go, and that's going to give me natural log y equals 1/2 times natural log x squared plus 1 plus 2 times natural log x minus 1. Okay, and I guess if I wanted to, I could distribute that 1/2. It would knock out the 2 on that second term. I don't think it's all that important. So now I am going to differentiate implicitly. All right. So that just means, for example, when I take the derivative of natural log y with respect to x, I have to use the chain rule. So the derivative of natural log y with respect to x would be 1/y times dy dx, or your Calc 1 instructor might have used y prime. Okay. And then on the right side, just differentiate everything with respect to x. Okay, so we have 1/2 times the derivative of natural log x squared plus 1 would be 1/x squared plus 1 times the derivative of x squared plus 1, which is 2x. And then the derivative of, let's carry that 2 along. And then the derivative of natural log x minus 1, that would be 1/x minus 1 times the derivative of x minus 1, which is 1. Okay. And now I think I will distribute that 1/2. It's just going to knock out this 2 and knock out this 2. So I wouldn't do this in a Math C class, but I think you all can handle it. All right. So now, kind of running out of room here, but we have 1/y dy dx equals x over x squared plus 1 plus 1/x minus 1. So there's just one more little thing we need to do. Let me make some space up here. Sometimes I go to the next page, but I think it would be easier to just do it like this. I need to multiply both sides of that equation by y. Let's do it in blue, why not? So y times 1/y dy dx equals y times x over x squared plus 1 plus 1/x minus 1. And then just rewrite that y back in terms of x. So remember what y was? It was natural log. Wait a minute. No, it wasn't natural log. It was the square root of x squared plus 1 times x minus 1 squared. And then you just keep this stuff. X over x squared plus 1 plus 1/x minus 1. Woohoo! All right, there it is. Okay. So it's still a little bit of work, but it's not any of that confusing chain rule inside of a product rule inside of a quotient rule. All right. That drives everybody crazy in Calc 1. So now I think this might be a good one for you to try. Every so often, you're going to hear me say, pause the video, try this one, and then when you're ready, unpause the video and we'll compare notes. Okay. All right, so now I am assuming that you have tried this problem. So here we go. First thing we're going to do is take natural log of both sides. So we have natural log y equals natural log theta sine theta over the square root of secant theta. And now this is the part where we use our properties of logarithms to simplify the right-hand side. So first I'm going to use quotient rule for logarithms, and that's going to give me natural log of theta sine theta minus the natural log of, it's the square root of secant theta, but I'm going to save myself a step and write it as secant theta to the power 1/2. Okay, so now there are a couple of things I can do. I can use the product rule for logarithms to write this next term as natural log theta plus natural log sine theta. And then over here, I'm going to use my power rule and go write that as 1/2 natural log secant theta. All right, so I think we've done everything that we can do with logarithms. It's time to differentiate. The derivative of natural log y with respect to x is 1 over y dy dx. Theta, sorry, with respect to theta. Even I get tripped up by that. Unfortunately, that is something that your online homework will mark you wrong for. If you put the wrong variable in there, it's just going to treat it as a wrong answer. Okay, so the derivative of natural log theta with respect to theta is just 1 over theta. The derivative of natural log sine theta with respect to theta is 1 over sine theta times the derivative of sine theta, which is just cosine theta. I had left that plus sign out for a second because, you know, sometimes it's going to be a minus. All right, and then over here we have minus 1/2. Derivative of natural log secant theta would be 1 over secant theta times the derivative of secant theta, which is secant theta tangent theta. All right, so I bet you see a few, you know, trig identities you can use there. You can certainly get rid of these secant thetas. I think I'll write that cosine theta over sine theta as cotangent theta. Okay, so I am getting ready to multiply both sides by y, but at the same time, I am going to pretty up a little bit over here. So we have 1 over theta, we have cotangent theta, and then here we have minus 1/2 tangent theta. All right, so final answer, dy dx is equal to y, which is theta sine theta over the square root of secant theta times 1 over theta plus the cotangent of theta minus 1/2 tangent theta. Done. All right. And that finally is going to take care of section 7.2. We'll see you in 7.3.